Welcome to day 2 of LHopitals. Here are different kinds of indeterminate forms today. This one, if we plug in 1 from the right, natural log of x goes like this. As we come at 1 from the right, natural log goes to 0, but 1 divided by smaller and smaller things actually goes to infinity. And the graph of 1 over x minus 1, that as we go to 1 from the right also goes to infinity. So this is infinity minus infinity. L'Hopital's does not apply to this because L'Hopital's is a very special case of a single fraction that comes up to be 0 over 0 or infinity over infinity. So we have the technology combine and make it a fraction by doing common denominator. Now, testing the limit of the numerator, the limit of the denominator. Individually, each one goes to 0. So L'Hopital's applies, and we can do the derivative of the top and the derivative of the bottom. And we get this, which is kind of messy. So I multiplied by x over x to get this down here. But plugging in 1, I still get 0 divided by 0. So we've got to do L'Hopital's yet again. Prove that it does apply, which it does. And now the derivative of the top is 1. The derivative of the bottom becomes this. And so plugging in everything today, infinity minus infinity is 1/2. Okay, now to do these next couple problems, I need to show you a thing that we can do with limits that we never explicitly teach you in the curriculum. To evaluate this limit, it looks kind of scary, but maybe the sign doesn't matter, doesn't get affected by the limit, so I'm going to push limit inside that function. Well, evaluating over that square root is kind of crazy too. Push the limit inside here, and then just look at this polynomial, this rational function. It's bottom heavy, so it's going to 0. So the limit is this yucky rational function in here goes to infinity. The function goes to 0. The square root of 0 is 0. Then sine of 0 is 0. So I'm going to use this technique of moving the limit in or out of a function as I wish. And we're going to do that to manage these kinds of functions, 1 to infinity, 0 to the 0, and infinity to the 0. Oh, this one is so exciting. Pause the video and write it down. So first thing, e and natural log undo each other. So I'm going to raise all of this e to the ln. And the reason that I'm doing that is I'm going to pull this stuff out and trade places with the natural log and the limit. And the reason I need to do that is I need to pull this exponent down. And checking to see if L'Hopital's applies, this is infinity times 0, which isn't helpful. That is not a place where L'Hopital's applies. So we're going to use this strategy, which you will need in some of the homework problems. And we're going to move this x to a denominator by multiplying by 1 over x. Well, 1 over x divided by 1 over x. So doing that, we do get now that L'Hopital's applies, checking the numerator individually and the denominator individually, and doing the derivative, we get this. Now plugging in infinity, we get 1. Please note our answer is not 1 because we had pulled out just this. You need to remember to bring that back. It isn't 1, it's e to the 1. So yes, in this case, 1 to the infinity for sufficiently large values of 1 is 2.7 and change. See if you can set this one up and try it. Pause the video. So e to the ln of that function, and I'm going to just pull out this portion, and I'm going to move the ln inside the limit so that I can move the exponent down. And again, I need the trick of multiplying by 1 over x over 1 over x. Checking my numerator and denominator separately. L'Hopital's does apply because this goes to negative infinity, that one goes to positive infinity. So do the derivative of the numerator and the derivative of the denominator. And we get, as x approaches 0 from the right, this thing goes to 0. And remember, it's not 0, but e to the 0, and e to the 0 is 1. Here's the last problem for you to work on your own, and then start the homework.